From the Library of Congress in Washington, D.C.
Good morning, everyone. I hope we're all ready for another set of interesting and insightful presentations about the history of science, medicine, and books. It's my pleasure to introduce Lilla Vekerdy, whom I've known as a historian and fellow curator for over 20 years. Lilla has been head of special collections at the Smithsonian Libraries since 2008. Previously, she worked at the Bernard Becker Medical Library at Washington University in St. Louis as rare book librarian for 13 years. Her research interest and publications are in the history of medicine and rare book studies, and often about the overlay of these two fields. Her presentation will discuss and place in parallel two illustrated books about science, the 1495 edition of Johannes de Ketham's Fasciculus Medicinae, one of my favorite early printed books, and an artist book from 2004 by Joyce Cutler Shaw titled The Anatomy Lesson. The first book was the direct inspirational source of the second one, and they were displayed together at an exhibition in the Smithsonian Libraries, Science and the Artist book. The comparison of the books reveals rivaling expressions of not just two, but three time periods. Within the Ketham work, ideas and ideals from the Middle Ages grapple with the Renaissance, and then both eras jointly appear on oppositional pages of modern depictions in the 21st Century Artist book by Joyce Cutler Shaw. Intending to untangle this threefold conundrum, the presentation touches on science, art, and poetry. Please welcome Lilla.
Good morning. Thank you, Michael, for the nice introduction. And thank you for coming out on a nice, snowy spring day. In this presentation, I will place in parallel two visually intriguing rare volumes. They are closely related and yet very different. One is an artistic medical book from the 15th century, while the other is a medical artist's book published in 2004. I will also use images of selected late medieval manuscripts and the artwork of Andrea Mantegna. Since we'll be skipping from book to book, from illustration to illustration, I tagged each image within every slide for reference. Please watch those small labels. The first book, titled Fasciculus Medicinae, usually spelled with AE at the end, in this edition just an E, the little bundle of medicine, was printed by the Gregorius brothers in Venice in 1495. Its first edition, published in 1491, is known as the earliest illustrated medical text in print and highly regarded for its artistic qualities. The book went through several editions in different languages in rapid succession. We will be looking at the second Latin edition from 1495, held in the Dibner Library of the History of Science and Technology in the Smithsonian Libraries. This relatively small collection, with its 35,000 rare volumes, is proud to hold more than 320 scientific incunabula, one of which is Ketham's Fasciculus Medicinae. The genre of the fasciculus is typically pre-modern. It is a compilation of various ancient and medieval sources. The text itself names Johannes de Ketham, presumed originally von Kirchheim, mid-15th century Viennese medical professor, as the compiler. Recent scholarship, however, has proven this proposition wrong. Offering no new proposition, though, the question, who compiled the book, is still open. This does not seem to weaken the established authority of the work, which is characterized in its frontispiece, shown here. The figure at the desk, Petrus de Montagnana, was professor of medicine at the University of Padua in the middle of the 15th century. A well-known physician, grammarian, and bibliophile, he is not the compiler of this book either. His role here is to represent authoritative knowledge in the person of a respected scholar transcribing or maybe translating a text that lies open on his desk. He is surrounded by books of Greek, Roman, and Arabic authors. Most of these books are medical classics. On the shelf, left to right, Aristotle, Hippocrates, Galen, Avicenna, Haliabbas, Rhazes, Mesue, and others, with the authors' names on the covers. The ornate binding of the Avicenna volume, placed strategically in the middle of the shelf, refers to Avicenna's role as princeps medicorum throughout centuries. Pliny the Elder's Historia Naturalis, open on the desk facing us, is an indication of the traditional importance of natural history in practical therapeutics. This illustration of the medical library of Montagnana denotes the most reliable sources according to contemporary medical knowledge. Established as these books were, their depiction, on the other hand, is inaccurate by nowadays standards. As you see, the artist is having a bit of a problem with the rules of perspective. However, a crucial moment is denoted here. The science and art of drawing the third dimension is in the making. The second book in our discussion is an artist's book titled The Anatomy Lesson, Conversations with Johannes Ketham. It was published in 2004. As an artist's book, this volume features the familiar aspects of the physical book, but renders its content visually with the liberty and endless possibilities of the fine arts. The result is a piece of art, which is still a book, and demonstrates a distinctive artistically emphasized relationship between text and image, form and content. The author and the artist of the anatomy lesson is Joyce Cutler Shaw, an active contemporary artist among the San Diego environmentalists. She started as a traditional painter and later turned to other media. An artist interested in science, she is fascinated by the works of Leonardo da Vinci and refers to him as major inspiration for her art. For years, Cutler Shaw was artist in residence at the University of California, San Diego Medical School, attended anatomy lab courses, namely dissections, and drew there. Drawing is a tool for the exploration of the world, she claims. The first version of the anatomy lesson was designed for the Science and the Artist's Book exhibition at the Smithsonian Libraries in 1995. For this exhibition, the libraries invited contemporary artists to choose and examine famous rare books from those that Bern Dibner, engineer, collector, and science historian, considered the 200 most significant works in the history of science. Inspired by the chosen old scientific volumes, each artist created a modern artist's book to be exhibited together with the original. Joyce Cutler Shaw selected the 1495 Chatham volume, and with a great amount of research, writing, and artwork, her new anatomy lesson took 10 years to appear in its final form. The physical structure of the two books differ significantly. The Chatham features a traditional structure, full-page woodcuts, and they face mainly text pages. On the other hand, the Joyce Cutler Shaw book, in her book, each gathering starts with a half title page, followed by 2 descriptive text pages, which then open up to a 4-panel view. On the left side, we see facsimiles from the Chatham volume, facing a new Cutler Shaw illustration and a poem written by her on the right. The individual segments or gatherings are bound together but act almost like separate books, reflecting the originally disjointed and only later compiled content of the Chatham book. Both books alternate ideas from 2 distinct time periods in different styles. In the Chatham volume, we see an interplay between medieval and Renaissance elements. In content, the book leads directly back to medieval examples and sources. Most of the medical ideas of the illustrations, we will see later, are also tied to the Middle Ages. Nevertheless, the artistic style of the Chatham illustrations represent predominantly the Renaissance. Note the flow of the garments, both the long academic robes and the non-academic short coats. Some feature here and there broken straight lines, more Gothic. Others handle the curves easily, more Renaissance. The architectural elements in the background, nonetheless, are in pure Renaissance form based on classical examples. Some of the figures evoke Andrea Mantegna's contemporary drawings, as you see with the arrows. Joyce Cutler Shaw shows the interplay between Renaissance and modern components, as she places facsimiles of Chatham illustrations next to her own. Her energetic drawings seem to rebel against the stiff Chatham images. In her plates, soulful modern-day figures appear with fleeting emotions and rapid movements, occasionally creating the impression of motion pictures. Let us now compare 4 pairs of corresponding images from the 2 books and see how different time periods, the Middle Ages, the Renaissance, and the 21st century, are woven into the fabric of the medical and artistic context. With this comparison, I would like to argue that a 500-year-old book can directly and beautifully inspire fresh content about science and humanity in the most modern style. The first image in our comparison is the vain man, a familiar character in most illustrated medical and surgical texts from the earliest times. The lines and words surrounding the figure point out the veins and arteries on the human body for bloodletting, the cure to cure various diseases. The ancient medical practice of bloodletting governed therapeutics in the Middle Ages and the Renaissance as well. The Chatham illustration has numerous examples in the medieval manuscript tradition looking almost like immediate predecessors. The figures of the vain man are quite dissimilar in the Chatham book and in the anatomy lesson. The Renaissance artist drew stationary figures with single contour lines. These are easy to render to a woodcut, and the body is presented in an idealized classical form and pose. In contrast, Joyce Cutler Shaw uses repeated and varied contour marks like we often see in Leonardo drawings. These ragged, uneven strokes are in constant motion, expressing fragile forms, referring to modern vulnerabilities. The intaglio method of photogravure well complies to this style. It may appear curious that Chatham's vain man doesn't really exhibit actual veins and arteries. Depiction of these were difficult, and the capillary system was not even known yet in the 15th century. It was first described by Marcello Marpighi in 1661. Familiar with that knowledge, the modern anatomy lesson, conversely, delineates the myriad of small veins and arteries and other anatomical intricacies in much detail. The following is from Joyce Cutler Shaw's poem for the Vain Man page, and I quote, "Originally, barber surgeons were authorized to use the knife for therapeutic bleeding as from the waist, for purging melancholy." So let us see now how bloodletting was supposed to cure melancholy. The presumed effect of bloodletting was based on the ancient humoral theory, which claimed that diseases were caused by the imbalance of bodily humors, such as blood, yellow bile, black bile, and phlegm. The four humors were associated with the four basic elements: air, fire, earth, and water, and corresponded with four qualities and four temperaments: sanguine, choleric, melancholic, and phlegmatic. Another ancient medical idea embodied in humanoid form is the zodiac man, or astrological man, often depicted in medieval and Renaissance scientific illustrations. With the signs of the zodiac on certain body parts, the figure symbolizes man's relation to the cosmos. In other words, the microcosm-macrocosm theory. Each body part is under the influence of a constellation, and the shifting patterns of the heavens cause changes in the body. Thus, the circumstances of the universe determine what can, should, or should not be done to the body in terms of medical procedures at certain times. For example, when the moon is in the sign of Aries, It is not safe to touch the head with iron or use medications on it. Joyce Cutler Shaw's Zodiac Man brings us into a new world. Instead of Catham's standing figure with the signs of the zodiac on his athletic body, here we see a skeletal cadaver lying in the pose and angle in extreme foreshortening, just like the famous Mantegna tempera painting, The Lamentation of Christ. The body is covered with a shroud. So, what is the significance of the shroud for Joyce Cutler Shaw? It covers and obstructs the body like the astrology-based microcosm-macrocosm theory obstructed real anatomical knowledge in ancient and medieval medical theory for several centuries. Lifting the shroud leads to new anatomical understanding, to empirical science based on observation, and not only on ancient written resources. The third figure in our comparison is the Wound Man. He has numerous representations in the late Middle Ages and the Renaissance, both in manuscript and print. This long-suffering character can bravely bear all possible wounds caused by all possible weapons, maybe because treatment is close, written right around the figure. The Catham Wound Man has much in common with the manuscript counterpart. Each has the same number of weapons hitting the body. The weapons are pictured in the same position, causing the same kind of injury. Yet, the artistic style is very different. The late medieval image features a schematic rendition of the human body in a somewhat awkward pose, whereas the Catham figure radiates naturalistic Renaissance harmony. I'm trying to start a video here. The modern version of the Wound Man in the anatomy lesson draws our attention from the wide array of early weapons and wounds to ultimate destruction. In her dramatic image, Joyce Cutler Shaw concentrated on humans' ever-escalating skill to devise more and more deadly weaponry throughout history, and especially in the modern era. Her illustration for this topic commemorates the tragedy of the victims of Hiroshima and Nagasaki. She conducted thorough research for these pages, which extended not only to scrutinizing rare books, but also visiting military museums. The last Catham illustration in our comparison is titled traditionally The Anatomy Lesson and depicts a dissection scene. It was not yet present in the 1491 first edition, but appeared as a new image in 1493 when Mondino dei Luzzi's anatomy text was also newly added to the volume. The appearance of this image and the new text marks a transformational moment. It represents that what we described as the lifting of the shroud by Joyce Cutler Shaw, namely the beginning of observational anatomy. The central figure here is the surgeon who exemplifies specific practical and professional competence, at the moment more important than the academic rank of the professor sitting in the background. It is also notable that the other central figure in this illustration is the student. This is Joyce Cutler Shaw's anatomy lesson illustration. She writes in her poem, "Anatomy by authority from a book, as a professor reads from his cathedra. As physicians and obeisant students stand below to watch a barber surgeon of the lowest rank to perform the cuts, until, dazzled by computerized cadavers, 3D artists spin their magic for students at their screens." And finally, the volume of the anatomy lesson has an intricate stitched concertina binding, which was co-designed by Joyce Cutler Shaw and Daniel Kelm. The brown paper on the spine is a continuous sheet folded in accordion style to create narrow tabs. Between two tabs, stitching fastens each gathering to 3 white linen bands going across the spine. On the front cover, a holographic image shows an 18th century lancet in 3D. The book then fits in an elegant metal box. Catham's volume is called A Herald in the Development of Science, and it marks the dawn of empirical anatomy. It is also considered one of the most beautiful books made in the first century of printing. Joyce Cutler Shaw's modern rendition is not only an equally beautiful reworking of the Catham book, but also a thought-provoking new creation through its own merit. She thus summarizes her artistic intents. "I am interested in new iconography without losing a sense of the physical self. More and more in media, we are fragmented, time eclipsed, dissolved, and scale shifted. We read ourselves in miniature on screens. I want to have a contemporary language that addresses this kind of fragmentation. And I also want to put it in the context that makes us aware of the whole." I think Joyce Cutler Shaw has wonderfully achieved these goals in her book, which was inspired by the age-old Catham. Thank you.
Good morning. I'm Catherine Blood, the library's curator of fine prints in the Prints and Photographs division, where I have the opportunity to work with everything from etchings by Rembrandt and Mary Cassatt to born digital artists' protest posters from the Library of Congress collections. Here on the second day of our symposium, Exploring Scientific Illustration and Intersections Between Art and Science, it is my pleasure to introduce artist and neuroscientist Dr. Greg Dunn. Dunn, who received his PhD in neuroscience from the University of Pennsylvania in 2011, has devoted his career to the fusion of art, neuroscience, and engineering to explore the mystery and beauty of the mind. Working with fellow artist and applied physicist Dr. Brian Edwards, Dunn has created an extraordinary, mind-bending, and extraordinarily beautiful artwork called Self-Reflected, which we will be hearing about in detail shortly. Dr. Dunn's larger body of work also reflects his admiration of Asian art and aesthetic connections between neural features and tree-like branching forms that suggest sumi ink scroll and screen paintings from Japan's Edo period. Other artworks carry titles like Cortical Columns, Neural Migration, and my personal favorite, Brainbow Hippocampus. In exploring Dunn's work, I started seeing connections with aspects of artworks I've had the opportunity to spend quality time with my own personal bias and interests, including artists' responses to issues of the body and health and the environment, for example. I thought of Eric Avery, an artist, printmaker, and longtime practicing physician known for his artworks responding to the AIDS epidemic and related to other infectious diseases, including performative on-site testing for diseases in artist settings. I also thought of Sandy Gellis and her Spring in the Northern Hemisphere. It's a series of abstract images with marks made by laying etching plates, exposing her etching plates to rain and other natural elements. And of course, we could go on and posit a multitude of kindred spirits from different approaches. But I came away feeling that Dunn's work really also feels utterly unto itself, with wonder and deep first-person knowledge as key ingredients. You can read media responses to Self-Reflected in Wired, The Atlantic, and The Huffington Post, to name a few. And when talking about the work in a filmed PBS segment called Greg Dunn Thinking About Thinking, Dunn explained that the reflective micro-etching technique that he uses was always in service to the idea of how to show the brain in all of its full complexity. He has also placed his impulse to depict the beautiful in science and nature within the larger art historical movement of naturalism, but using modern technology toward a neo-naturalism. Deeper still, Dr. Dunn invites us into a shared state of meta-awareness in considering his art, saying in his words, Self-Reflected is designed to reflect what is occurring in our own minds as we observe this work of art, reminding us all that the most marvelous machine in the known universe is at the core of our being and at the root of our shared humanity. Now, to guide us on this journey, please welcome Dr. Greg Dunn.
Thank you very much, Catherine. Thank you to Mark and Stephanie and the Library of Congress for having me here. And as excited as I am to be here, I have to say that the most exciting thing for me right now is that unlike in the dream that I had the other night, I actually remembered to put pants on this morning. So I'm pleased at that. So I have a lot to say, so I'm going to get started here. And I want to talk a little bit about the intersection of art and science and what my definition of it is. This is an oil painting, incredibly. And this, in my opinion, is a science experiment. Why? If you had 100 sufficiently skilled artists, the results of their experiments would be identical because they're referencing external reality for to collect the data to be able to make this work of art, which is exactly what you want when you're doing an experiment in the lab. Science is about describing the external universe, whereas art, if you want to think about it in terms of this spectrum, I think is more about bringing something out of our subjective experience into objective reality for others to be able to appreciate. So this Gerhard Richter abstract piece might have been, you're asking an artist, paint what frustration feels like. And every single artist is going to paint something a little bit different because this is not something that we can really reference through external reality. And almost every single thing that we do all the time is some blend of those two things, like this Craig Mullins piece, where he clearly understands the rules of how the universe works, perspective and reflectivity and this sort of thing, but brings us to a place which doesn't actually exist. And I think that this is the most fertile territory for both art and science. And scientists, I think, are constantly intuitively turning inwards in order to gain inspiration for their experiments as well. So how does this kind of translate into scientific imagery? Well, this is a photomicrograph. If you're infusing fluorescent proteins into a section of tissue, this is pretty much as verbatim as you're going to get in terms of being able to analyze the anatomy here. Whereas this would be the other side of that spectrum, a representation of the brain done in watercolors by Holly Warren here. But I'm going to go here and a little bit on a limb and say that Santiago Ramon y Cajal, who is widely recognized as the godfather of modern neuroscience, he won the Nobel Prize in 1906 for Spain for some of his work kind of elucidating the world of neurons and neural circuitry. Is you can see here on the right that you have some of his slides immediately juxtaposed with his illustration of those slides. And at this time, a lot of researchers were using a technique called camera lucida, which is a technique that enables you to sort of project the image of a microscope onto a surface so that you could trace it more or less. And Cajal used this only sparingly. And what I don't think is really appreciated as much these days, and it's a little bit of a difficult comparison to make because imaging technology is so vastly superior to what it was in Cajal's time. But when you're looking at a slide, it's one very small slice of a much more complex system that you're looking at. These neurons are snaking around in 3 dimensions. You're looking at a lot of different slides. You're bringing in the context of your other knowledge about neuroscience in order to interpret what's happening. And Cajal, I think, rightly recognized that making an illustration, that caricaturing this circuit was actually a more effective way to communicate these difficult points than was showing a photograph verbatim. And when I think about, what the average person thinks about when they think about their own mind, the thing that is at the most fundamental aspect of who we are as people, the sort of depressing answer is that this is probably what most people think about it, is a translucent blue walnut with lightning coming out of it, as is sort of the illustration meme du jour. And this is another kind of common one that you see, neurons floating in space with little bolts of electricity traveling between them, which is illustrating the point that neurons communicate through action potentials, which are indeed darts of electrical potential which travel along their axon, which is the part that communicates activity to downstream neurons, and that receives these electrical inputs through their dendrites, which is their kind of branch-like structure that they use to collect information from. And they also kind of look like those robot octopuses from The Matrix to me. So this is telling you a little bit about the brain. This is just a tiny fraction. The brain has 86 billion of these things, and that's only the neurons. There's a lot of other stuff going on as well. So in terms of being able to elucidate for the average person what it is that we're dealing with here, I think these communicate a very specific point, but not a particularly broad one. And a lot of people are familiar with the scientific imagery here. This is a functional magnetic resonance image. And this is telling you, while you're in the scanner, what might be happening in your brain when you're picking your nose, for example, in this. That's the brain area that controls that. And this is telling us that the brain is compartmentalized in terms of its activity. And I suspect that these types of images were also key in communicating the incorrect conclusion that we only use 10% of our brains at any, really in totality, which is so utterly ridiculous as to, it boggles the mind. If the most energy-hungry part of our body was only using 10% of its capacity, then evolution would have evolved that out instantaneously. It is completely incorrect. So this is now more of the kind of fluorescent scientific imagery. This is probably, some of you may have seen this type of thing, and this is starting to belie the true complexity of the anatomy here. Of course, this is not telling us what it looks like in 3 dimensions, and typically microscopy is only able to show us a little bit at a time. And it's not able to show us how the brain evolves in time and what it looks like in time, which is really one of its most incredible aspects. And of course, we're all familiar with what the meat of it looks like. And I remember holding a brain in graduate school and being surprised at how little you can actually understand about it just by holding the thing in your hands. Like all the vein diagrams, as Lou was talking about earlier, pointing to all the different regions, it's very difficult to tell what's going on. It's just this kind of peach and lighter peach color kind of intermixed in this way. So I became kind of inspired to represent the brain in different qualities and methods when I was in graduate school. And one of the reasons is you're just exposed to so many gorgeous pictures of the brain all the time. And I've always been a fan of Asian art too, which is part of this context. This is one of my favorite paintings, the red and white plum blossoms. This is from the Edo period in Japan. And this type of aesthetic was also happening in China and in Korea. And one of the things I love so much about this art is typically that it's sparse. There's a lot of negative space. And they tend to emphasize the incredibly beautiful and spontaneous branching patterns that you would find in nature. One thing that's difficult to paint, that's difficult to do in this type of painting is that your brain is not good at generating randomness. It tends to want to build patterns out of things. So actually, the Zen approach is to paint and to try to release your mind from its instinct to make those types of patterns. But what I found when I was looking at neurons all day is that these branching patterns are absolutely in common with neurons, and the reason is that nature has encountered a similar problem at different scales. In the world of neurons, the goal is to splay your dendrites out in order to collect as many synapses as possible, whereas a tree, of course, is trying to collect as much light as possible. A lightning bolt is trying to discharge its electrical potential down to the earth, and it finds the path of least resistance. That's essentially what this shape is. It's the path of least resistance, which is controlled by other detailed variables depending upon the system. What I didn't have, unfortunately, for the astronomers in the audience, of which there are a few, is that the orientations of galactic superclusters also look like this neural shape. This is a fractal. And fractal is a common shape which repeats through different orders of magnitude. So some of my initial work, like this piece, Basket and Pyramidals, which is a simple ink painting on gold leaf, is as much a declaration saying that the world of neurons fits very cleanly into the canon of Asian art, but also that the world is made of fractals. Because somebody who doesn't know about neuroscience might look at this and say, oh, this is trees, but it's kind of not like trees. What's going on here? And to have somebody be in that state of uncertainty for a little while is kind of the point, that there's a comfortable kind of presentation of the idea that then stretches you as you consider it a little bit more deeply. And to further this point home, these are some of the scrolls that I painted and still paint every once in a while. This one on the left is of the retina. Here's one of astrocytes and one of the emerging complexity and kind of opaqueness of complexity in the brain. And this is to further drive that point home between the connection of these two worlds. I began to experiment with reflectivity in my art as something akin to form and color in order to emphasize you can draw the viewer's eye to specific things when you're using reflectivity. And it's not something that has been very deeply explored in the history of art. So unfortunately, I don't have a video of this piece, but when you move around it, those white stripes, or these lighter stripes right here, would actually move depending upon where the light is. My sister kind of describes this as looking like the scales of a trout, is the idea. And it puts things into and out of silhouette. Here's a piece of the spinal cord. And Pedro was saying yesterday, which I thought was a really good point, is that it's nice to be able to give somebody familiar context when you're describing something that's unfamiliar to them. And so this piece I kind of stylized to look like the blue iridescence of a morpho butterfly, as the anatomy of this structure is definitely reminiscent as such. Catherine mentioned that I'm really interested in the idea that your brain has evolved to investigate itself. Like, what a weird concept that is. And this piece is really exploring that idea, that this is a multi-electrode chip. So right now in neuroscience at the forefront, you stick these electrodes into the brain and are reading the brain activity of this neural network here. And you're reading essentially these electric pulses which are going between the neurons. And this piece is stylized to look like almost an alien abduction, to call, the point being that there is this sort of strange relationship to the brain wanting to understand itself. This piece is called Axon Pathfinding, and it's about the chaos that emerges when you have many, many axons growing towards their locations at a similar time, and the kind of chaotic patterns which emerge from that process. This piece is called Hippocampal Formations. The hippocampus is the part of the brain that controls learning and memory. And this is equally inspired by the hippocampus itself and by the erosion patterns in the desert in Jordan. was looking at some satellite imagery, and sure enough, rain hitting mountains and then shedding off into the rivers down below is also nature's solution and a path of least resistance that really resembles this type of neural form. So this is kind of a hybrid, and again is commenting on that fractal nature of the universe. And I do occasionally do things which are not related to the brain. This is a recent piece called Photosynthesis, which is about a simulation of how nutrients in water would be transported in the vasculature of leaves. But this next piece, Self-Reflected, is, I think, a categorical difference in how I had been illustrating the brain and painting it up to this point. And it emerged from an existential frustration that I felt in graduate school, where you're working on a project that's pretty complicated. You make a breakthrough on it, and you feel like you finally understand something about the brain. And lest your hubris take you to a place where you really shouldn't be, it's always a good idea to be searching the literature and find out what other people are thinking about that, at which point you find 600 papers that you had never considered. And then you consider that the amount that people actually know about the brain is a fraction of what is actually going on. So to be able to communicate the incredible awe and beauty that I saw in the brain, I wanted to invent a technique that would be able to kind of communicate that emotionally and perceptually to people. So what you're about to see is a reflective microetching, and this is the world's most complex depiction of the human brain. This is what's happening in your brain at this moment. This is not a digital piece of art. This is a physical object hanging on the wall, which is being illuminated from overhead by various light sources. This is the collective simulated activity of 500,000 neurons at once. And this object is made of millions and millions of tiny etches that are microscopic in the surface of this gold plate. The color that you're seeing is not inherent to the piece. The color comes from the fact that there are these different colors of light source which are above the piece and are reflecting off of the surface. So really the aesthetic innovation of reflective microetching is that color has now been turned into an infinite variable. And this is a demonstration of when I'm passing kind of a sheet across the various lamps that are over the piece, and you can see that each one of those colors has essentially a channel of reflectivity which it's optimized towards. So this shot now is really the meat of what the project is. This is what it is in animation mode when the light is strafing over the surface. And you'll see in the lower left-hand corner here coming up that this is where we are zoomed in to the piece. And right now we're in the cerebral cortex, which is that walnut-shaped covering of the brain. This right here is the parietal cortex, where you're integrating your vision and your movement. So you're reaching out to pet a cat or to punch somebody in the face. This is the somatosensory cortex. This is where you would feel sensations on your skin, for example. Right now, coming into the motor cortex, this contains some of the largest neurons in the body. And these are the types of calculations that are being made when you're playing piano, for example. And you're learning and you're refining these circuits in order to optimize what it is that you're doing with your brain. And you can see how the neurons are arranged in these kind of laminar type structures, particularly in the rear parts of the brain, where they communicate both vertically and horizontally to integrate information. And as we continue here into the frontal cortex, so we're about right here right now, right behind the forehead, you'll notice that the activity becomes more chaotic here. There's a lot more inner neurons which help to refine local circuitry. This is the part of the brain which is controlling logic and planning. And this is what differentiates us from the higher primates. this region of the brain spins on its own, even without any sensory input. This is what thinking looks like. And these neurons are sending their information down back into the central brain structures, which tend to be the more evolutionarily distant types of very basic emotional movement type centers. And now we're getting into the basal forebrain, where you have a lot of structures involved in motivation and reward. That big burst that you'll see at the bottom of your screen right there is what it might look like when something pleasurable and unexpected happens, or like snorting a line of cocaine would be the activation of that region. We're now in the basal ganglia here, the caudate nucleus. This is where you integrate your kind of logical perceptions, your emotions, your memories, your sensory perceptions in order to plan your movements. And now we're in the thalamus, which is the very, very center of the brain. And there is so much stuff happening here, so many things being routed in and out. And the way in which this region gates information allows us to pay attention to things kind of more or less. There's a lot of important regions in here involved in attention and arousal, and these large tracts coming down here, which are coming from the motor cortex, will become the spinal cord and are executing the movements that you're planning kind of in your higher order cerebrum. A lot of these structures here in the brainstem are very basic to life, like breathing and hunger. And now we're getting into the cerebellum, which is right here at the very back of your brain, which is kind of a brain in and of itself. This involves movement and proprioception, which is how you sense your body in space. And this region by itself contains half of the neurons in your brain. There are 50 billion neurons in this region. We're coming back up now the spinal cord, and we see the colliculi here. This is for auditory information and for visual information, respectively. And then we're coming into back around to where we started. This is the lateral geniculate nucleus of the thalamus, which is receiving information from the optic nerve, from the eyes, which is sending information here to the primary visual cortex, where these neurons are calculating very simple things about your visual system, like where all the angles are, for example. And that gets passed up into higher order visual cortex here. So that is what self-reflected looks like. And of course, I want to credit my good buddy and collaborator, Brian, who also worked tirelessly on this project. So what is a microetching? So I mentioned again that previously that a microetching is millions of tiny little etches in the surface of a metallic surface. This is a very, very close-up photo of what that looks like. You can see that whatever is a specific color is made up of etches of a specific angle. So the blue is at a different angle than the red is. But again, the color is not inherent in the surface, nor does the color come from light splitting off of the surface like you would see in a hologram. It's due to the fact that the lamps are different colors. And the consequence of that is that when you move around this, those colors are going to be shifting, which is how we are be able to engineer the lighting in this. And this is what the surface looks like under a scanning electron microscope. This is a 1200x image showing you that we have these wave-like reflectors. And this kind of doesn't look like anything here. Like the business end of this is so abstract compared to what the macroscopic perspective of it is. And just quickly, I wanted to show you this. So this is really the primary data which goes into the creation of this piece. Just look at this little structure right here that's going up here, this little dendrite. You can see that the angle changes gradually as you move across this surface. When a light moves over that surface, the consequence of that is that you're going to get this angle is going to be optimal to where the light is at a very specific point. So you'll see a bright spot originate here and then travel along this structure, which is how we're able to achieve those animated effects using this technique. And around this time, and I'm forever grateful to the National Science Foundation for believing in us to give us this grant to fund this project, because we're essentially funding a visualization. And the thing that we told them is, look, we're in the golden age of neuroscience right now. I consider it of great philosophical importance that people have a more enriched understanding of what their brain is. And the goal of this project is to change the way in which the average person thinks about their brains. And they indeed rewarded us with the grant, and we were very grateful for that. So one of the first things that we had to decide is what we're going to show. And we decided to show a sagittal section, an oblique sagittal, so it's coming through your head like this. Because there's a lot of really interesting structures. You can show things to their completion in there. It seems like a good region to begin. And this is a representation of the best data that was available at the time for the human brain. Compared with the resolution that we were trying to work with, this was woefully inadequate. So this piece was not a scan. It's so far from that. It's made entirely from scratch, and I'll tell you more about how that was done. And one of the things I really want to emphasize too is that there was a lot of kind of balancing the art and the science in this piece. You know, what are the things that are crucial to be able to show verbatim, and what are the things which could be bent a little bit in order to make a point more strongly? And one of the things that was really nice, actually, in some ways at least, is that the state of the data in the human brain is so poor compared to what it would be in mice or rats or even like a rhesus monkey that we just had to fill it in, you know, with our best guess in a lot of cases. So this is a map of where all the gray matter regions are. Gray matter is where the cell bodies are. So each color here is indicating a different functional region. This is a rough map. It's more complicated than this. But with the help of some of our neuroscience students at the University of Pennsylvania, we went through each of these regions and just did a ton of research in the primary literature as to what the neurons look like, what they're connected to, what their firing patterns are like, blah, 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 so that we could get this accurate. And as there were no really good pictures for what all the neurons looked like, and because I wanted to infuse more of an artistic sort of flair to this, almost an abstract expressionism using the technique I'm about to show you, we decided to paint all the neurons by hand. So this technique was invented to get over the fact that your brain, again, is terrible at generating randomness. When you try to paint neurons with your hand, you're going to put a node every 2 centimeters. And you're going to find that rule, and you're going to undo it, and then some other rule is going to emerge. With this technique, you're allowing nature to make fractals just like it wants to do. You have loose control over it, but the turbulence of the air and the inconsistency of the fiber direction of the paper is going to cause that ink droplet to split up into these beautiful fractal-like patterns, which are highly reminiscent of neurons to begin with. So we painted about 150 different categories of neuron and a few examples of each, scanned them into the computer and turned them into vector objects, which we then used to paint the gray matter down. So we painted down about 1 million neurons using this technique. So that's how the gray matter was made. But the white matter is in this image right here. Whatever is black stained in that image is what the white matter is. And the white matter are the collections of axons traveling long distances, carrying information between the different brain regions. And what's impossible to see in this image is that this is very, very beautiful structure, very complicated, of many highways kind of traversing one another. And so we had to send our friend, Dr. John Piles, into the future with this time machine to bring this image back to us via diffusion spectrum imaging. This is a render of a magnetic technique that's similar to MRI, and we filtered this data set to be in the plane of our data set that we're interested in here. And this became then the inspiration to paint all of the vector shapes of the axons by hand as well. So this was done mostly in Adobe Illustrator, and this is an example of 2 of these sets. These are cortical sheets that we used to input into the piece. So now we have a lot of neurons and we have a lot of axons, but there is no connection nor causality sort of between these circuits. And as complex as it was already, this has already taken over a year. This next part is really what brought the piece to life and infused the 3rd dimension into it, because microetchings essentially allow you through reflectivity to impart a 3rd dimension into the art, and in this case it's time. So you have a neuron, it fires an active potential, it travels down its axon. You have a group of neurons that's communicating with a downstream group of neurons via their axons. So this is one step of choreography, as we called it. One set of neurons communicating with the next downstream set of neurons. And this is what my artist palette looked like at some point. So lest you think that as an artist I was walking into my studio and flinging my cape off and saying, what am I going to create today? I sat down in front of this damn computer and it was basically coding at some point. There's about 30 variables controlling the speed of the impulses, whether or not the neurons are firing as a group or individually, et cetera. And there's about 600 lines of this choreography here. So this is much more like taking some artsy-fartsy hippies and forcing them to do the most brutal corporate taxes that have existed. So this was definitely a bridge between art and engineering here. I don't have a whole lot of time to go into this, but what I wanted to say with this slide is, again, we're dealing with time here. So when we're programming a circuit, neuron A is going to fire at time equals 0. Neuron B is going to fire at time equals sometime later than that. And when we're working with two-dimensional images, the way that we encode that time is through hue space, through these different colors. So neurons which are firing early in the animation will be a red color. Then you'll see the orange neurons, then the yellow ones, then the green ones, blue ones, et cetera. So as the light moves over it, you're not going to see these colors in the final piece. You're going to see the neurons which are red in the computer data as being illuminated when you're standing all the way to the left of the piece. And then if you were to walk from one side to the other, you'd see the orange ones, the yellow ones, et cetera. So this is a close-up of what this render looks like. And this is what the whole brain looked like after, I don't even remember, it was days worth of crunch time for this algorithm. To give you a sense of what the complexity of the math is like here, it's similar to logistics companies solving, we need to deliver 100 packages and we need to find the optimal route to do it, which is a notoriously challenging math problem. There's a lot of different variables at play there. And we're doing this for 500,000 neurons. So that took a good long time. And then the question is, how do we turn this into a physical object, right? Because we now have this data in the computer, but we need to turn it into to physical microetching. We have the data plotted out in 2 dimensions, and we have this 3rd dimension of color in the piece. So the thing that you must know, the very first thing you need to know, is where the light source is going to be. And let's just choose any pixel randomly on the surface of the microetching. We know based on that pixel's color where we want the observer to be able to see it from. So we know then what the position of the viewer is, and we know the angle that we need the light to come off of that surface at. Knowing these 2 angles now, this angle to the light source, this angle to the observer, we can now extrapolate the angle at which we need to make a little tiny mirror at that spot. And rather than make bevels like in a diamond, which would be reflecting a ray of light to a very specific point, we're actually making little cylinders which splay the light out more, so that if you're shorter, if you're taller, you can see the reflections coming off of it. And we're actually, for each pixel, making a little grid of these cylindrical reflectors. So the rendering at the end of this is we've increased the resolution by a factor of 10. And this is what it looks like in great detail here. So you can see the outline of a neuron here, which is made of one specific angle of hatching. Those are printed onto transparencies at ultra-high resolution. You would never be able to see that with your naked eye. The feature size in this is about 100 microns, which is about as big as an average human hair. Then we use those transparencies to do photolithography. This is how computer chips are manufactured and how etched plates have been made in the past as well. So you start with a sheet of steel. We laminate a photoresist, which is an ultraviolet light sensitive polymer on top of that, and then we put our transparency on top of that. So of course in the transparency you have regions which are printed and regions which are clear. When you turn on the UV light, the light penetrates through the clear region and polymerizes, makes that part directly under here hard. Everything else underneath the black printing is protected by that black printing and it remains soft. So turn off the UV light, remove the transparency, dip the whole plate into a basic solution, and it eats away anything that was underneath those black lines. And we can do this in very, very high resolution. So you're using light and chemicals and transparencies to essentially burn this image into 3 dimensions. Here's some images of laminating the materials. This is in the clean room in my studio. This is the UV light source right here. Here's the plate being exposed on the wall. And so now this is what the photoresist surface looks like. That's what the etching is actually done in. It's this dark purple, which is reflective but not super reflective. And because this art is completely based upon reflectivity, we need to brighten it up a little bit. And we learned that gold leaf is the perfect solution to this problem, because gold leaf is super thin. It's 200 nanometers thick. So it's so much thinner than our relevant feature size that it's not going to fill in all of our topography and wreck it. It's malleable enough that you can force it into all those tiny little crevices. It's never going to tarnish, and it looks awesome. And everybody likes gold. So it was the perfect engineering and aesthetic solution to this problem. This is the initial kind of lining up of the plates, which then needed to be cut down in the final step. And here's Brian here when we developed this method to cut these plates to within about a hundredth of an inch of one another so that they would line up seamlessly. And this is an assembly of 9 of those plates on the floor of my studio on the first day that we assembled. And Brian stressing out about some tiny little detail that nobody would ever see. We built a light source for the piece where it's installed at the Franklin Institute in Philadelphia so that we could get all these effects. These are some of the students that worked on it with us and us. This kind of looks like the Ghostbusters car now that I look about it right here. And this is what the image looks like just under a single white light. But again, a microetching has so much flexibility in how it's viewed that this is only a fraction of the amount of data which is really in it. You can put different colors of light around it. This image just won the National Science Foundation's Science and Engineering contest last year, and it's surrounded by 3 or 4 different lights. And here's just some other quick kind of close-ups of what the image or the piece looks like. And color is kind of cool here too, because color is indicating what is firing at that particular moment. So all the red neurons in this image would be firing at the same time. So there is data encoded into the colors of these images. And this is what it looks like in situ in the museum. And I can guarantee you that there were many times during the production of this piece, for the 3 years of my life it took to make this thing, the hardest thing I've ever worked on, where I was asking myself, why am I doing this? You know, like what's really is going to come of this? And the thing that really kept me going was imagining a kid going into this museum and standing in front of this gigantic gold glittering object and have the light strafe over the piece for the first time and the kid to look up at it and just say, wow. And then for them to jump up and down and run off to the next thing and mash buttons somewhere else in the museum. Or for them not to, or for them to look at it more deeply. But you know what? I don't care if people look at this piece and they don't remember that the thalamus and the cortex have recurrent connections, or they don't understand where the cerebellum is. I don't care about any of that. All that's there if you're looking for it. The thing that's most important about this piece is that it makes that initial emotional impact. We learn through our emotions. It's the most important thing we can do to communicate effectively with people. Excuse me. And to that end, one of the most important parts that I learned in grad school was this idea that, so the visual system is ridiculously complex. I mean, we're very visual creatures. We navigate the world with it. And we use vision to keep us safe, right? We need to be constantly analyzing our environment and make sure we don't get bitten by a snake, for example. And milliseconds matter here. So when light hits your retina, it goes through the optic nerve, through the thalamus, and into the primary visual cortex, where you have, you're processing, again, things like basic angles, you're combining those into form, you're looking at whether motion is happening, you're looking at color, and these are higher order structures where the information gets passed to. But this is being processed largely in parallel, which is a more efficient processing technique. If you were to process it in series, where each step is contingent on the data being complete from the previous one, it would take a lot longer to do this. So you need more machinery to process in parallel, but you can do it faster. Basic form and silhouette information is being siphoned off of this pathway and is being sent to your limbic system, which is basically your emotional systems, the amygdala right here. This is before you're seeing it. This is way subliminal. You're not actually consciously aware of what's happening at this point. It's being processed through the amygdala for emotional valence. It's making sure that there's nothing happening in your visual field which is a threat. Because if there is, you want that data to be there as fast as possible, which is why you get it there in an as early a state as possible. Then that data is sent back into your visual system and is combined with the rest of what's happening in your visual system to actually make this world that we're seeing on a daily basis. But the implication of this is that you are not seeing verbatim reality. You're seeing what your emotions are coloring for you. And I'm sure many of you can understand that the implications of this are extreme. And we don't have time to talk about the societal implications of this, but in the context of art, what's important is that your silhouette has got to be strong because it's being analyzed for emotional character before anything else is even happening. Illustration and making fine art can really teach you a lot about what your subject material is too. And I learned some interesting kind of meta realizations from essentially building a brain. This one in particular, normally people think about brain development as taking place with genetic and epigenetic components. So genetics, of course, are the genes that we get from our parents are hardwired DNA sequences which control who we are, which control how neurons grow and find their destinations. And then you have epigenetics, epi meaning outside of genetics. This is how our environment controls the expression of our genes. It's basically the software of how we are functioning. So you can have a gene which is folded up in its DNA in such a way such that the machinery can't access it. So the genes can be turned on and off via these epigenetic mechanisms. So via these two mechanisms, you have billions of axons growing towards their targets in early development. And try to imagine what it's like at a place like St. Mark's Square in Venice, where you have many inputs into this huge plaza, which is just packed with tourists constantly. And they're all trying to get somewhere. And they're all bumping into one another, and they're all generally getting to where they're going with a large amount of chaos happening at the same time. This is what's happening in early development as well, such that if you had even an identical brain in an identical environment, that the randomness involved in this process, particularly when you're talking about billions of objects moving against one another at the same time, means that the brain is going to develop differently every time. At this resolution you're looking at it, you might not be able to see a difference, but the devil is definitely in the details here, where an axon might arrive a little bit off target. And if any of you have built complicated things in your life, you know that as you approach perfection, once you get that last 1% of details, that last 0.01% of details, or even more detail than that, the ability to reach that perfection becomes fleeting and basically impossible, and particularly when you're working with a system this complex. So the brain knows this, and it is compensating for it. The brain overconnects early in development. It's at its maximum potential early in development. This is why your damn kid can learn words in a foreign language way faster than you can, because their brain is much more plastic, it has way more potential. Then the brain perfects itself depending upon what input you give it. So in early life, if you're reading a lot, if you're playing outside a lot, if you're learning a new language, something like this, it prunes away the irrelevant connections and leaves you with a much more kind of refined template than you would have had otherwise. And now, I guess kind of in sum, just talking about what I try to make my illustrations to be, and what I think that Eleanor really did very well yesterday in some of her pieces, particularly her Mars map, I thought really encompassed a lot of these very well, is what components you need in a truly effective image that can change people's perceptions. I mean, obviously the scientific content's got to be there, and it's got to be right, and it's got to be clear. Having it be emotionally engaging is also extremely important because people have got to care about it. There's way too many things to learn about in our world right now. We're consuming more data at this moment than we have in history by orders of magnitude. So your thing had better be interesting and emotionally engaging. Adding your own kind of aesthetic and style to it can also help to differentiate it a little bit. And one that like a practice that I use too is to use what's out there as almost a negative inspiration in a way, to use it as a constraint to further refine my thinking away from what currently exists in the world. Because there are a lot of terrible ideas in here. And one of the reasons I've become better as an artist is because I've been better at figuring out what is a good idea and what isn't a good idea. What do I spend your time on? I mean, I don't think that it's a measure of success to relentlessly throw yourself at a problem until you solve it. It's much wiser to figure out if a problem has potential early on so that you can prune it off and save your time other than waste your life. So when all of these things are there, and like I said, with some of Eleanor's pieces yesterday, this was me at the center of the Venn diagram. Because that's how the world moves ahead. The humble scientific goal of Self-Reflected was to blow as many minds as possible. That was what we were really going for. So if you want to read more about it, there's a bunch of articles about this. This is some of the places that my work is hanging as well. And I wanted to thank sincerely Mark and Stephanie and everybody at the Library of Congress for giving me the opportunity to speak here, and all the scientists and artists and physicians who contributed their knowledge and expertise to this project, as well as the students, of course. In the long-term goal of this project, again, is to transform the way in which the average person thinks about the brain. So some of the next steps are in getting these pieces into museums around the world, and not just science museums. I want to get them in contemporary art museums, because I think that this term neo-naturalism is one that's I'm trying to throw around a little bit about. This is a step forward in the sense that I want to be able to show things that the average person just can't see with their naked eyes. I mean, we as scientists are incredibly privileged that we get to use these sophisticated tools to see what many can't. And I think bringing that to the public's imagination and attention is an important goal. So I'll be around afterwards if you guys want to chat. I have a sample of a micro-etching to show you if you're interested. And thank you so much for listening.
Morning, everyone. My name is Shelby Calloway. I'm the historian at the U.S. Department of Agriculture's Natural Resources Conservation Service, and I'm delighted to be here at this wonderful symposium and to get to introduce you all to our next speaker, Dr. Catherine Newell. Professor Newell holds a PhD from UC Santa Barbara and currently serves as a professor of religious studies at the University of Miami in Florida. She has far too many honors for me to list them all right now, but just one that seems especially relevant is she's also the 2017-18 Larson Fellow in Health and Spirituality here at the Library of Congress's John W. Kluge Center for the book. Dr. Newell is an outstanding scholar of both the phenomenology of religion and the history of science. Her research focuses on the conjoined histories of religion and science, particularly the way in which scientific paradigms frequently owe their genesis to a religious idea or belief. Her forthcoming book, which intersects with several areas we've discussed at this symposium, is tentatively titled The Wheels of Titian, Faith, the Future, and the Final Frontier. The book traces post-World War II American zeal for space exploration back to 19th century religious discourse surrounding belief in American manifest destiny. The volume focuses on the artists, historians, and scientists who popularized space exploration by framing the conquest of the final frontier as a modern religio-cultural legacy of the conquest of the American West. I'm sure you're all going to want to rush out and buy it as soon as it becomes available after you hear this talk. So please join me in welcoming Professor Catherine Newell.
Good morning. Thank you for that. And thank you for having me here today. And I want to say especially thank you to Stephanie. She told me about this symposium, I think it was this summer, and I said, I want to come. And she said, you want to present. So here I am. So it's very exciting. So what I want to talk about today is a little bit having to do with my forthcoming volume, and in particular the question of where we got the idea that space is the final frontier. Because it's not something that maybe would occur to us naturally to look at, say, the surface of Mars and say, let's go there and explore. On you maybe, not me. But I think for a long time we've had a narrative that this comes from science fiction, the most famous split infinitive in TV history: seek out new life and new civilizations and boldly go where no one has gone before. And that's at least partially true. I found this letter to Willy Ley, one of the people I'm going to talk about today, in the archives at the National Air and Space Museum, being thanked by Gene Roddenberry himself, inviting him to come visit the set of his very successful television show, saying, "We're looking forward to meeting one of the pioneers who made a space travel television show possible." So again, these intersections of science, art, culture, popular culture. But Gene Roddenberry did not invent the idea of space as a frontier. And in fact, to understand more about why we think of space as our frontier, it's useful to look back to images that we're actually surrounded by all over here in Washington, D.C. We're going to see a lot of them today. And this is actually one of the later images I'll talk about. It was I think it even just started life as a lithograph in 1872. And it was meant to illustrate, and it's very problematic, and I know that we have people fleeing before the power of the image of Columbia heading west from the east, bringing with her technology like railroads and telegraph wires and chasing all of the scary people out of the way. But it's useful as a representation of this concept of manifest destiny, because even though we associate manifest destiny with this kind of conquest of the West, it's also alive and well in and around particularly the history of space, and most particularly for my purposes, what the people I call the space proselytizers that even preceded the American space program were revitalizing with their work and their art. So today we're going to be talking about these two gentlemen. On the left we have Chesley Bonestell, actually sitting in front of his background for the film Destination Moon that he designed. And next to him is Willy Ley. Bonestell was an architectural designer. He became a movie special effects artist. We'll talk more about that. And Ley actually started his career in Germany as a rocket expert and science reporter. And together they are more than the sum of their parts. I believe they created one of the most influential books on space exploration possibly ever written. It was written for lay audiences and published in 1949 and billed as a preview of the greatest adventure awaiting mankind, with texts and pictures based on the latest scientific research. And we'll get more into it, but Ley and Bonestell wanted to introduce the possibility of the exploration of space, but the idea of exploring space in 1949 was so implausible to the average person who maybe wasn't engaged in science fiction that the two of them had to connect space exploration to its more terrestrial cousin, the historical conquest of the American West, we saw in that John Gast painting. So the idea of exploration and the eventual settlement related to the exploration of outer space in general, and for the purposes of this book, our solar system in particular. So what was at stake in their idea of conquest of space wasn't homesteads and settlements, but actually the act of exploration itself. So I'm a scholar of religion, and we love having ideas to frame what we do so we can point at them and say, well, I'm not saying it, they're saying it. So the person I am using to kind of frame this conversation today is Edmundo O'Gorman in his 1961 book, The Invention of America. He said that the old notion that imprisoned the world within the bounds of an island had been overcome with this kind of so-called discovery of the New World, that essentially it wasn't just that Columbus sailed away in 1492 and suddenly a new world was discovered. It was more that when he came back, there was a reframing of our understanding of the world, and that was the invention of America. And I just want to point out that this image, I just found out the other day, is actually, it might have been done for the Adler. I meant to look it up, but it's obviously an image of Earthrise from the moon done by Chesley Bonestell, and I think it was 1951 or 52, and it's going to be at the Air and Space Museum next year. So they are in the process of flattening it out and making it look pretty again, because it's been in storage for a while. But, so O'Gorman's idea that the old nation that imprisoned the world within the bounds of an island had been overcome, the possibility was open of accepting as parts of the world not only all that is contained in our planet, but also other planets and any other heavenly bodies. So again, this expansion of our understanding of who we are and where we are isn't just limited to what O'Gorman calls a lump of cosmic matter that already existed, but can be given a new life and be discovered in the case of America, or become explored in the case of the solar system, and that itself is a kind of invention. So, in order to close the gap between the remote physical frontier and the anticipated imaginary frontier, the method of discovery needed to be a new technology that merged the fantastic with the scientific. So what we're going to talk about today is the ability of scientific illustration, specifically the science of space art, to introduce space exploration, to reveal the future so that one does not need to believe without having seen. And our space program's founders were pretty clear that the space program was one of the biggest institutionalized acts of faith in all of human history. But I choose to talk about the scientific illustration of space art because Bonestell and Lay were not only able to capture the scientific elements of space exploration, but also tapped into a revitalization of American faith in manifest destiny, this belief that Americans are destined and called to explore and settle the frontier, in this case, the frontier of space. And just a shout out from everybody's favorite public scientist, that Carl Sagan was one of the first to say that Bonestell's images helped him understand what it was he was actually looking at and looking for. So we're going to be looking at mostly his images between 1944 and 1955 as an invitation to explore and discover new worlds. So go back to 1944 with this issue of Life magazine. It was published on May 29th, 1944. It was a week before D-Day. And 2 weeks after this issue, this cover would feature the very famous photos by Robert Capa of the beach at Normandy. And this issue, you can find it online. It's pretty ordinary. It's full of war news and black and white photos of the European front. But at the back of the issue, there's this article titled "Solar System. It is modeled in miniature by Saturn, its rings, and 9 moons." And even the advertisements in this issue reference the war effort. So this article seems a little bit off topic, and it's actually the exception that proves the rule. It is virtually the only 6 pages in the magazine that don't mention the war. And in contrast to the issue's black and white photos, it's the only portion of the magazine to have full color pictures. And so the article's purpose is revealed in this first paragraph, which I'm sure you can't read, but it promises a visit to the planet Saturn, where the pictures show the changing aspect of Saturn and its satellite family as it would appear to a traveler hopping towards the planet from moon to moon. These astronomically accurate pictures are photo montage paintings made by Chesley Bonestell, Hollywood miniature set designer and amateur astronomer. So we heard a little bit about Bonestell yesterday. But he actually started his career as an architect. That was a compromise with his grandfather, who said, I think people have had this conversation with their kids from the beginning of time, I will only pay for you to go to college if you do not study art and study something practical. So their compromise was he studied architecture. And as we'll hear, he eventually left architecture to become a matte painter in Hollywood, but he's remembered today primarily as the father of modern space art. He was born in San Francisco in 1888. He lived until 1986, so he saw the whole span of space exploration and space science be revealed over the course of his almost century-long life. And throughout that long life, his two great loves were art and astronomy, and he liked to joke to his friends that he was an astronomer to his architecture friends and an architect to his astronomer friends, so kind of living between these two worlds. And again, he eventually left architecture. Probably one of his most famous contributions to architecture as a designer was the exterior of the Chrysler Building in New York City. It's one of his better known projects. But just before he left architecture, he worked with Joseph Strauss, who was constructing this mad idea following through this mad idea to put a bridge over the Golden Gate Street in San Francisco. And Bonestel was recruited to work with Joseph Strauss et al. Because Strauss was an architect and an engineer, and he couldn't explain to the directors, i.e. the money, where the money allocated to the plans were supposed to go. Strauss thought in architectural renderings, but Bonestel thought in pictures. So Bonestel's drawings of how the project would progress, and we can see the sinking of our pillars here and the ghosted outline of what will eventually become the bridge, were put together to give to the board of directors, but eventually were repackaged as a booklet that was available to be purchased at newsstands called The Golden Gate Bridge, a Technical Description in Ordinary Language. And I love this pamphlet because it's Bonestel in a nutshell, because it's this tremendous architectural engineering triumph that is rendered in these clear and really nice to look at images that include tiny people that are showing kind of the scale of the project that is being attempted. And this was actually the last thing he did in architecture, more or less. The bridge was completed in 1937, and Bonestel left San Francisco for Hollywood to work as a matte artist. Before we had computers that did a lot of these things for us, and this is still a skill that shows up in some movies, there were artists who were skilled painters that created backgrounds for foregrounded live action shots. And the matte artist's job was to render a background that was textureless. It was supposed to look like the film in which it was being merged with. And this is from Citizen Kane. This is one of the first films that Bonestel worked on. And in a history of a book that's the history of matte artistry, they actually quote various matte artists who still can't believe that Bonestel managed to match up the shadows with the image in the door. So this art is still responsible for some of our favorite, well, my favorite, scenes in films, and is still considered a very technical and very important skill today. But again, one of the first films that Bonestel worked on was Citizen Kane. And he was particularly interested in Orson Welles' opening shot of Xanadu, which is Charles Foster Kane's castle. It begins at the gates of the castle, and through a series of dissolves, we move, some people probably remember this, we move through the gardens, then to the zoo, then to the front door, and then we kind of float up to the window of Kane's bedroom. And in each shot, the castle gets bigger as we get closer to it, but maintains its aspect ratio. In other words, it illustrates a journey, and this is what gave Bonestel the idea for a journey to the planet Saturn, because as a fan of astronomy, he'd been incredibly frustrated with the current status of space art. It was either scientifically correct, but maybe not that lively to look at, or it was fantastically lively and moderately inaccurate. So He wanted to use his technical skill as an architectural designer and his artistic skill as a matte artist to do his own version of space art and essentially improve on techniques that people had used before. So this is why life promises us a visit to the planet Saturn, even ending on the planet's surface. So we start out on tiny Phoebe, where Saturn is still far away, but the view of Saturn from Phoebe is almost exactly proportional to the perspective of the moon seen from Earth. And at this point, Phoebe was thought to be Saturn's most distant moon. We now know that that's not true. But from there, we move to Iapetus, where, please note, we have tiny explorers here tootling around the canyons there. And then the one to rule them all, the Saturn seen from Titan, which is probably not only Saturn's best known moon, but this image made it into your program. This is almost definitely Bonestell's best known painting, and another artist actually called it the painting that launched 1,000 careers, because so many people, like Carl Sagan, were inspired to become astronomers, astrophysicists, astronauts, engineers, space artists, and ironically, Carl Sagan was one of the scientists responsible for the discovery that Titan's atmosphere is actually opaque, so you would never have this view to begin with. So, oh well. From there we go to Dione, which is known for its volcanoes, so we're looking at Saturn from inside of a lava tube. Our last moon is Mimas, where Saturn is so close that it fills the entire sky. And you can actually see the shadow of Dione there and the shadow of the rings being cast on the side. And finally, we go to the surface of Saturn. We're actually looking up through the methane clouds, standing just a few degrees north of the equator. And to get this perspective, Bonestell stood himself at 15.5 degrees latitude in Saturn's northern hemisphere. And as Willie Ley later explained, if you were on Earth and wanted this view of Saturn's rings, all you would have to do is go to Guatemala and look up. And this is an image by Ron Miller. He's a contemporary space artist. But what was perhaps the most extraordinary element of the paintings was the stylistic choice that enchanted Bonestell's first admirers. So in the foreground of two of these paintings, as we saw, there are tiny people. They first appear here on Iapetus. They're also again on Mimas, and they're wearing space suits that are pretty prescient for 1944. They have shielded helmets and oxygen packs. And all 5 of these figures are depicted inspecting this rocky new frontier. So even though one very unimaginative editor at Life felt to explain that they were put there for perspective, what Bonestell was doing was adding more than perspective. He was bringing back to life the Hudson River School of Painting, an artistic movement that faded with the closing of the Western frontier. And Bonestell's assertions that his paintings were based on fact and not fiction placed him in the legacy of these romantic landscapes of the 19th century of painting, and has actually led some to call Bonestell the last Hudson River School artist. So beginning in the Hudson River Valley, and with the fathers considered to be Thomas Cole. In the decades leading into and out of the Civil War, these paintings evolved with the time to share the cultural enthusiasm for exploration and expansion, but also expressed a nationalistic belief that nature was both a source of spiritual renewal and a location of cultural and national identity. And here we have, this is actually the explorer Ferdinand Hayden and presumably a Native American guide standing on the edge of the Grand Canyon of the Yellowstone. And of course you can see this painting just down the road. But we know Bonestell was a fan, or we can conjecture that he was a fan, because he frequently reproduced elements of those paintings in his own. And this is from another article in Life magazine about the origins of the Earth. But the scope of Bonestell's paintings of Saturn's moons and the diminutive foregrounded figures set against a backdrop of a frontier are tropes in these paintings of the American West made by some of the school's most famous artists, such as Thomas Hill, Frederick Edwin Church, Albert Bierstadt. Note the tiny train coming through the mountain there. And especially Thomas Moran, but I just wanted to show really quick. So this is an image that Bonestell did in 1949, the same year that Conquest of Space came out. And this gentleman in the red shirt here is actually Chesley Bonestell Sr., so a little picture of home. So artists like Moran traveled with government research teams to explore the Yellowstone, the Grand Canyon, the Rockies, and brought back landscapes of vast panoramas, which included scientifically precise renderings of regional flora and geology. And Moran's images were significant not only because they encouraged further scientific study and ultimately the preservation of places like the Yellowstone, for their remarkable scientific curiosities full of freaks and phenomena of nature, but also because they revitalized the sense of a calling to settle and explore that had been lost in the spiritual crisis of the Civil War. And that spiritual crisis was answered with calls to explore God's new Israel, in the language of many of these proponents, and double down on their sense of a faith and a calling to conquer the frontier. But in the same way that Moran's paintings of the Western frontier comforted a nation unsure of their next step after the Civil War, Bonestell's images were a step towards revitalizing a sense of faith and calling and an evocation of a nostalgia for the exploration of the Western frontier, and actually to show viewers something beyond the horizon of the Second World War. This is actually a quote from a gentleman from Ohio writing a letter to the editor about 3 weeks after these images appeared in Life, saying, "If mankind in its frenzy should succeed in utterly destroying itself, the destruction would create not so much as a ripple in the great universe of which we are only an insignificant part. May Life publish more about the universe that we may learn from its law and order to avoid war." And they also, arguably, these paintings evoke what Elizabeth Kessler calls the astronomical sublime, an extreme aesthetic experience that threatens to overwhelm even as it affirms humanity's potential, that makes us feel small but connected to a larger and wider universe. And apparently Life realized that that was true of these paintings, because they paid Bonestell the equivalent of about $250,000 today for the rights to them. But these paintings set Bonestell on a path that eventually led him to our other hero for the day, Willy Ley. He was born in Berlin in 1906 with a passion for exploration, and he actually recounts in one of his books that when an elementary school teacher asked them what they wanted to be when they're grown and why, he said he wanted to be an explorer, and the teacher said, "That's not a real profession. Think of something else." But Ley was undeterred. He was actually, as he described it, born in the shadow of the Museum of Natural History in Berlin. And he spent his whole life looking especially into, as he put it, such corners as others had neglected through the natural sciences and physics. And when he went to university, he couldn't actually figure out what he wanted to study, and he took on subjects ranging from astronomy to zoology, which sounds like a bad joke, but was actually what he was trying to study. But his curiosity and passion eventually took him beyond the neglected corners of science and even beyond the ends of the earth. And he, at the age of 20, published his first book, The Journey into Space. That was the first of many books written by Ley that attempted to translate a dense and convoluted science for an ordinary reader. So he was taking other things that were being published at the time that were basically just equations and turning it into a narrative that anybody could pick up and understand. And his first book was successful enough that he was asked by Fritz Lang, the writer and director of the 1927 film Metropolis, to act as a technological consultant for his new film, Woman in the Moon, or By Rocket to the Moon, at the age of 23, so that's pretty decent. But Ley eventually came to America in 1934. He had been one of the founders of Germany's famous spaceflight society that would eventually be sort of subsumed into the German army and start building V-2 rockets. And he left in part because he was of Jewish heritage, but also because he was dismayed by the idea that these beautiful rockets that he was helping build and design were going to be used as weapons. That wasn't really what he wanted to do, so he moved to the US to begin his career again as a science writer and journalist. And his first and most famous books were about, as he called them, exotic zoology. But by far the bestseller published in English in the 1940s was his, I believe it was 1942 book, Rocket, Missiles, and Space Travel. When it first came out, nobody was aside from a small select group of people, were very interested in rockets. About 3 months after the book premiered, Germany had their first successful tests of the V-2 rocket, and suddenly everybody was very interested in how rockets worked, and this became an overnight bestseller and made him very famous. But even though he was suddenly asked to write about and to give interviews on the purpose of rockets, he refused to say that they were solely for the purpose of blowing up London and Paris, that actually after the war everybody would see that we would be able to use these rockets to explore our solar system, that they weren't a weapon, they were a mode of transportation. So in 1945, Mechanics Illustrated asked him to essentially tell us how this would work. How would we take a rocket to the moon? And they said, we'll get you somebody to illustrate this so it makes sense. And this was how Lay and Bonestell met. So this was the first article to feature Lay's prose with Bonestell's paintings. And Bonestell actually later, it's the favorite theme of science fiction is no longer a fantasy. Latest advances in rocket research will make space exploration a distinct possibility. So again, this idea that rockets will be the way in which we get to the moon. And moving beyond what he did for the magazine, Bonestell actually created with Lay's help, he created a trip to the moon that begins on Earth, kind of slingshots us towards the moon, comes in for a landing over Aristarchus crater, and lands not too far away from Mount Pico, and points out that the landscape is broken rock because there's no water to erode river valleys. But, and here we have, very hard to see, but there are explorers again. Yes, the moon is not this mountainous, but it makes for a lovely picture to think that this is what it looks like. But what was especially significant, or I think significant, about this particular journey was that it's easy to forget that at this point, no human had seen this view. We were still about a decade away from some of the first satellite images of the Earth surrounded by space. And it would be another 25 years before the crew of Apollo 15 took this image in 1972. And it's accurate, we'll say, all but for the upside-down martini glass. It's maybe not part of the original Apollo missions. But Bonestell had eventually become so in demand that he left, more or less, working in Hollywood, and began to produce so many images that they reached a critical mass. He didn't know what to do with them. A friend suggested, why don't you write a book with your friend and mine, Willie Ley? So the two of them worked out that the book would be a guided tour of the solar system by rocket. So in chapter 2, Ley tells us we are in New Mexico, waiting for liftoff. We're going to use the Earth's gravity to slingshot ourselves towards the moon. And here we're flying over New York City. You can see Central Park down there. We will reach the moon and spend a week or two there to explore a little bit. This image became pretty iconic when it was more or less the inspiration for George Powell's science fiction classic Destination Moon. He even borrowed the rocket, named it Luna, and asked Chesley Bonestell to do the background. And my favorite thing about this film is that it ends with the title card that this is the end of the beginning. So this is just our first dip into space. But back to our explorers in the conquest of space. They are, again, spending some time getting to know the surface of the moon, making astonishing discoveries in the surface of rocks there. But because there is less gravity on the moon, it is easier to create liftoff. The plane of the solar system is such that it allows us to move around the sun and go land on sunny Mercury. where we have to wear, the temperatures are so high that our visiting explorers are forced to wear asbestos suits, because we should all wear our asbestos suits when we go to Mercury. We then pass through Venus's dust bowl, where actually Earth is the morning star. You can see the morning star right there. We hop right over the Earth and head to the moons of Mars. Poor little Deimos, before heading down to tour the famous canals of Mars. And this image in the book is accompanied by the note that it was checked for color by Dr. Edison Pettit of Mount Wilson and Palomar Observatories. So again, the idea that we are using the best scientific knowledge at our hands in order to create these images. But from Mars, Lay takes what he tells the reader is beyond the realm of the dwarves, Earth, Mars, etc., where just as the fairy tales always existed, there is the kingdom of the giants. So our first stop is the moons of Jupiter. I think this is Europa. And then we head to the surface of Jupiter, which is depicted as frothy with hydrogen lava and liquid ammonia. After we go to Saturn, same images appear in The Conquest of Space as were in Life magazine. Then we go to Uranus, Neptune, and then out to lonely little Pluto, back when it was still a planet, before it was fired. That is so far away from our sun that it appears as only a slightly larger star on the horizon. And this jaunt around the solar system led Robert Heinlein, in a review for the Saturday Review of Literature, to half-jokingly, half-sincerely call this book the Baedeker of the solar system. It was a huge bestseller, and in thinking about not only its purpose but also its effect, it reminded me, and I think has reminded others, of Captain Cook's voyage in 1768 when he took a young naturalist with him named Joseph Banks, who was only 24 years old. He volunteered to accompany the crew and came back with an entire ship stuffed with plants, flowers, fish, insects, birds, mammals, reptiles, shells, rocks. He returned back to London to unpack and catalog these spoils and to eventually publish his journals, so his narrative of his time, in a place that nobody in England, for the most part, would ever see. But the apotheosis of his collection actually was nearly 1,000 botanical paintings by Sidney Parkinson, a young Scottish Quaker artist who accompanied the voyage. Banks also created almost 1,400 drawings of plants that went on to be published separately. But what Parkinson and Banks did was bring back these images of Pacific Islanders, of new harbors, new horizons, and brought back a new world that was invented, again, through the process of the interpretation of the hordes of information that Banks stowed away in his house. So the books and discoveries that came from Banks's collection and Parkinson's drawings proliferated and popularized the pursuit of natural history, both as a calling unto itself and as an accumulation of facts, figures, statistics, characteristics, and data from around the natural world. In short, what Banks et al. Did was become what historian Richard Holmes calls in his book, The Age of Wonder, a kind of chorus figure or guide, a scientific Virgil, who was warning young men and some young women away from the life of a quiet country gentleman and encouraging them to go out and see new life and new places for themselves. So Banks ended up becoming an example to the young, curious, passionate explorers of a generation of his disciples. And this was more or less the effect that The Conquest of Space had on a generation of people in 1949 when it was first published. They had grown up more or less in the shadow of 2 great world wars and the Depression, and to see these new horizons served as an incredible source of excitement and hope for the future. And Ben Bova, very well-known science fiction writer, said that as a Strong League writer, it was as if Bonestel had gone out to Mars and the moons of Saturn to survey the territory I wanted to write about. Long before the first spacecraft arose from Earth's surface. Bonestell had been there, and his vision of these worlds is still the most vivid, the freshest, the one that excites me even now. Arthur C. Clarke, in a contemporary review of, Clarke and Bonestell would actually publish together at one point, but he was relatively unknown at the time, or becoming better known, and in a review for the Saturday Review of Literature, I think it was, he said, Mr. Bonestell's remarkable technique produces an effect of realism so striking that his paintings have often been mistaken for actual color photographs by those slightly unacquainted with the present status of interplanetary flight. So, and here are brave explorers hopping around in the low gravity of one of Mars's moons. But the book made Lay very famous, made Bonestell very famous, and Lay used some of this momentum to work with other, again, space evangelists to put together a series for Collier's magazine. And it was a series of articles that ran from 1952 until 1954, included people like the great ringmaster himself, von Braun. There's Bonestell, there's Lay. There was also the astronomer Fred Whipple, physicist Joseph Kaplan, Heinz Haber, a medical doctor, and they all, for this first issue, wrote a series of articles, each of a couple thousand words. And the premiere issue is titled Man Will Conquer Space Soon, and opens with an editorial titled What Are We Waiting For? And the short introduction asserts that on the following pages, Collier's presents the story of the inevitability of man's conquest of space. What you will read here is not science fiction, it is serious fact. And so with that, we begin our errand into the wilderness with von Braun's article, Crossing the Last Frontier. And the title itself is one of just a dozen references to space as the last frontier, a literal space for civilization, settlement, and technological conquest. Von Braun closes the article by explaining that Americans are ready for a journey to, quote, man's oldest and last frontier, the heavens themselves. Lay wrote on the topic of one of his favorite inventions, which was the space station. If this looks familiar, it's because it was the inspiration for the space station in 2001, A Space Odyssey. But he actually uses his article to explain not only that this station will be a useful platform for acquiring scientific knowledge, but that it is also a good position from which to move from Earth's orbit out to the other planets to continue to explore. And this image is by Rolf Klepp, it's not by Chesley Bonestell. But the next issue in October 1952 is about a trip to the moon, and it begins with this fleet of 3 cargo ships carrying between 10 and 20 crew members apiece. The ship is actually meant to be assembled in space, and features some of the ships from the original article and the space station kind of hovering nearby as the finishing touches are put on the lunar ships. So we have our space station. This is from the original article. These are the space taxis that are bringing our crew up to work on and assemble their ships that will take them to the moon, where they will land and set about exploring for about 6 weeks. They will turn these ships into essentially habitats, and from them will emerge their transport vehicles that will take them all over the lunar surface. And they'll actually leave these, according to the plan, they will leave some of these things there for the next expedition to the moon. And I love this image on the right because it is just indisputably prophetic. This is the eagle taking off from the surface of the moon 17 years later. So after further issues dealing with the practical questions of how humans will fare in space, Collier's turns to humanity's most ambitious endeavor yet, to Mars. So on April 30th, 1954, von Braun's article, Can We Get to Mars, was the anchor piece in a 3-article issue on the exploration of the red planet. And in the 2-page spread, we have the Mars fleet assembling 1,075 miles above the Earth, and there is our space station, and again, our space taxis. They ready themselves to, again, slingshot themselves around the Earth, head out to Mars, where they reassemble above the Martian surface and descend to land on the North Pole of Mars, and will drive down to create habitats, which will be their base while they are exploring Mars. And lest we forget to pay our debts, there's plenty of Bonestell to go around and continue to inspire us all. This is from The Martian, the 2015 Ridley Scott film, and I said that that image of Saturn seen from Titan is the most famous Bonestell image. It actually shows up in the movie. It's in, you can kind of see it behind Sean Bean's head. It's in the head of NASA's office hanging there on the wall. But again, inspirations reassert themselves through generations. This final image, if it will ever come up, when it appeared in Collier's in 1954, summed up the hope not just for a space program, but for a new frontier. Weapons have become ships, and heroes are geologists. We've taken technology and science to their furthest points. You can see this image in the Air and Space Museum there, and you can see this image across the street. This is one of Moran's paintings that I think is a pretty unmistakable homage represented in the Mars image. The Collier series of articles didn't just inspire Collier's readers, it actually inspired Walt Disney, who had been looking for content for the Tomorrowland portion of his new amusement park. And his producer, Ward Kimball, suggested that he look at the Collier's articles. So over the next 2 years, Disney and Company produced a series of essentially live-action versions of these articles that starred Von Braun, Lay, and Heinz Haber. The first is Man in Space in 1955. It was, and I think it was earlier in the year. And there is Haber, Von Braun, and Lay. It was followed at the end of the year with Man in the Moon, about the first excursion to the moon. And this is Lay's space station redesigned so they wouldn't get into trouble with Collier's for reproducing them. But, and eventually, Frontierland and its mirror of Tomorrowland, mirrored across each other, would be anchored by their respective forts and by the rocket that Lay helped Disney and Company design for. And it was a little ride that you could go on a trip to the moon, around the moon, and on the back of the moon there was some kind of alien base there, and yeah, everybody's favorite trip to the moon. But 2 years after the Disney specials and the Collier's articles, theologian Paul Tillich wrote in his famous book that man is driven towards faith by his awareness of the infinite to which he belongs. An act of faith is an act of a finite being who is grasped by and turned to the infinite. So what I love and find myself wondering is the invention of space an example of being grasped by and tuned to the infinite? Essentially, is the exploration of faith an act of faith by a finite being here on this earth looking for new frontiers? Because in the same way that 19th century Americans couldn't support expansionism or believe in manifest destiny before they'd seen the frontier rendered by artists like Moran, 20th century Americans couldn't believe their new frontier or the value of space exploration without Saturn seen from Titan or the surface of Mars. But the question my work picks up on is the imagining of space something that can be revitalized again? And on August 12th, 2012, the whole world, more or less, tuned in to watch what NASA had billed as 7 minutes of terror. And a highly produced animated short, the landing of the Curiosity rover on the surface of Mars by a sky crane, very James Bond, had circulated on social media, introducing the global public not only to the lander's purpose, but the planet for which it was designed to explore. And this image was the first one that went live on the internet. Curiosity has its own Twitter, her own Twitter feed. And so this image of her foot some said was the substance of things hoped for, and there was much rejoicing, not just amongst the scientists, but also amongst the public. And I just have to say, I love this guy's face right here. These are people who spontaneously gathered in Times Square in New York City to listen to essentially the broadcast that was happening from the Jet Propulsion Lab in California after having watched this animated version of Curiosity landing on Mars. And when the rover was said to have landed and that tweet went live of the foot of the rover, the whole group just exploded with joy and apparently started chanting things like NASA, NASA, and science, science. But for me, what I think is exciting is that it's an expression of collective effervescence in which an entire tribe joins together to celebrate a totem, in this case, curiosity, which then becomes sacred through the collective gathering of the clan. So I think scientific illustration can help the whole world partake in science, in space exploration, and in a new frontier. So oops, that was our friend Curiosity. By situating his paintings in the tradition of the Hudson River School, Bonestell connected his project to that of artists like Moran, who illuminated the Western frontier in the previous century. And perhaps Lay's desire to explore space revitalized the sense of a calling to explore these new frontiers in new ways, such as sending rovers like Curiosity to the surface of other planets. So I believe Lay and Bonestell illustrate the way in which, as Weber put it, ideas become effective forces in history. They created an enthusiasm for the frontier so powerful that just 25 years after Bonestell's images of Saturn appeared in Life magazine, 2 Americans walked on the moon. America's faith was rewarded. The frontier had been conquered. So, thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.